Sergey Belov, representative of STTT Group in Russia. He will speak about automatic object detection and identification on the remote sensing imagery of the sea surface. Hello. So we have key with the number 305 attached to it. Somebody forgot it there. Distinguished colleagues, I would like to present to you a small information outlook about the project undertaken by the three organizations: the Institute of Programmatic Systems of the Russian Academy of Sciences, located in the town of Pereslavsk-Zalesky, OST Group, and Rakurs. The work is funded by a small grant, which was given to us by Ministry of Education and Science. Now it has been reorganized. And the main purpose of this project was to develop, in fact, to verify the theory and to develop methodology in what way can we, using the remote sensing means, to find schools of industrial fish to help fishing boats to find them in the sea. And for the biologists, it would help them to monitor the conditions of those schools of fish to make sure that we have enough of them. If we go back into history, in the Soviet times, the aerial fish exploration was used quite actively. In other words, from an airplane from the altitude of about 1,000 meters, people with simple observation devices like binoculars could see the fish, and experienced observer could even tell what species of fish is there. So in theory, this is quite feasible, but it's clear that if we use, say, UAVs, we can also do this. But we decided to see whether we can do it using satellite imagery. Again, I can tell you that in Soviet times, our fleet was totally centralized, so the aerial exploration was economically justified. Now it is not so. That is why the use of remote sensing means, or satellites, might deliver some additional effect. For us, the task was to see whether it can be done at all and how, if ever. Now, speaking about economics of this, the cost of operation of a fishing boat is about 500,000 rubles per day. That is why economic effect is to help fishermen to quickly find these big schools of fish. If we do the imaging of the sea surface, we can see there, first of all, the actual object of our main interest, the industrial schools of fish, as well as other objects, like, for instance, mammals, birds, plankton fields, algae, artificial objects, sea garbage, oil spills, boats, and other technical facilities, as well as many elements of non-biological origin, like shallow areas, slicks, where there is no water turbulation, which can also be seen on the images, and shadows of clouds. Naturally, that all of these things will interfere with our trying to observe the object of our interest. On this image, the fish schools look like this. They are of linear shapes up to hundreds of meters. Usually they have a dark brown color and sometimes typical texture. Of course, we can detect biological type fish which swim at the close to the surface. But fortunately, most of the industrially caught fish, like herring, sardine, and some cods, belong to this type. That's why in theory and practically we can detect these fish using remote sensing devices. Considering the sizes of these schools, naturally we'll have to use high resolution devices with a resolution of about 1 meter. In the same manner, on these images we can see the interfering objects like algae, technical debris, technical facilities, and boats. As long as the fish schools, our objects of interest, on the high resolution image are quite small, first we need to decide where to do the imaging. We cannot simply do image the whole sea surface. It wouldn't make sense. That's why for selection of this area we use two methods. First, in the areas of concentration of fishing boats. If we simply use the system of automatic identification of fishing boats, which is available openly and commercially, we can see where different fishing boats are located, and as long as they're all concentrated there, it means that the fish is there. That's why we need to do the imaging right there. The second idea is to try to build dependencies on indirect principles, where industrially caught fish schools were because of the indirect indicators. For instance, biologists have such parameters which are directly linked to the existence of fish. Simply speaking, the idea is quite straightforward. Fish needs to eat something, and usually it eats on zooplankton. Zooplankton is what feeds on phytoplankton. The phytoplankton needs oxygen, and here we have such dependencies, simple ones and sometimes more sophisticated. Of course, to build real models of dependency here would be quite difficult, and here we are assisted by the methods of artificial intelligence, which allow us to detect such difficult and sophisticated dependencies. Here some of the parameters which can be detected by various data acquired from different meteorological satellites, like from the MODIS cameras, Aquaterra, and from our meteors, and so on. These methodologies how to calculate those parameters are quite well known. When we decide on the area where we'll do the imaging, first of all, the percentage of images there where we can find our objects of interest will be quite small. And first of all, we need to use some automatic method to sort out the images by detecting the ones which would be subject to our subsequent processing. We do this also by the method of using AI intelligence and taught neutronic networks, which will help us sort out and filter empty frames from the ones with some objects there. Then, after selecting the frames of interest, we do detection of boundaries of the object, do then the classification, identifying the objects that we are interested in, and like concentration of fish and analyze them. As for the detection of borders, this is quite a difficult task because different objects can overlap with each other. Like sometimes there could be cloudiness, tides and boats. But for this, Pereyaslav Institute, using the AI center capacities, because they've been working on different methods there, they have their own in-house methodology. And these two slides are all about that. I unfortunately cannot comment on anything more than what is already listed on the slides. If you're interested in the details, I can get you in touch with the authors of this methodology. Then when we identify some of these objects, we need to classify them. Once again, we are less interested in the classification per se. We are more interested in that identification and separation of the fish objects that we are interested in from other irrelevant subjects. For that we use the trained neuron networks, and along with the classification we form a mask which will help us separate this object for its subsequent more detailed analysis. We use neuronic networks, unrollable ones, and they consist of the big number of levels of processing, more than 100 processings for each level, more than 100 masks at each level. Each one of them detects typical objects, and the last level of this information is summarized, and they do the likelihood classification. As a result, we have examples like these masks for schools of fish, for algae, and for garbage. We do the assessment of the quality of the acquired results. For that we use these well-known parameters, which shows how well we detected the object sites, and the Descartes method showing how well the mask covers the actual object. In fact, here there are some peculiarities of this work. I don't want to speak about it now, but while we were doing, this is actually the last slide already, almost last slide. While we were working on the methodology, we were working on a rather small selection that we had. We have a couple of dozens of images there. Besides, we use also specially synthesized images. When from a real image we change its parameters, and we see what it would look like if we captured it at a different angle and with different lighting. We use this to train our neuronic network. So based on this rather small sampling, we acquired the parameters which are shown in this table. It is quite clear that the fish can be identified quite well. The algae is more difficult to detect. But the work is still ongoing, and now the biggest task for us is to ensure more accurate big sampling, and we want to ensure that we have 1,000 to a couple of thousand images to recheck these results on a bigger sampling size, to train our neuronic networks and to improve those algorithms depending on the acquired results. Hopefully we get good result, and then we'll report on it, and after the completion of this work we'll report on that. That's it. Thank you. Questions now? Yes, please. You use optical range images, right? We use optical range images for detection of those biological parameters that I mentioned. They have radar as well. When you said that the fish is supposed to flow next to the surface, have you tried to use hyperspectral images? Because they can go deeper on the water. Maybe some other things might be involved there. And surface-wise, how many meters deep can you detect it? For the detection of all these parameters, we use mostly hyperspectral images. Like Modi's camera is fitting our needs quite well. Also, some European apparatus are quite good. And here we use mostly hyperspectral technologies. And as far as how deep they are from the surface, we try to detect them because we can detect them. So they swim about a few dozens of meters from the surface, and they're still seen on the optical images. Here, the nature is helping us because they're swimming deeper. When the water transparency is higher, and when it is less transparent, they're getting up because phytoplankton also needs light to grow. This way, we can still see through the transparent water. In fact, it could be up to 100 meters, but usually it's 5, 10, 15, maybe 20 meters, and they're quite visible. The main problem is a totally different thing, because we need high resolution images, and the fish and such industrially caught schools of fish are not swimming next to the coastline but somewhere deep in the ocean. Nobody's going to capture seaside images at this resolution. So we have to organize dedicated missions for that because of the organizational things. Now we're in the exact moment of time when we have to risk and do a dedicated high-resolution capture to collect more test materials. Any more questions? I have a small question. Tell us, please, according to your estimates, how quickly do you think it can be done? Because these schools of fish are migrating, how do you perceive the organization of detection of all those schools of fish? And then you will process it right away, and you will tell the fishing boats right away where to go. In theory, I see no problems here because all this work is done automatically. That's what I mentioned in the beginning. Now, our captains are saying that we're planning to go in that direction. We can operationally order the imaging and get it, to get some more or less quick work from our constellations, the way it is organized here. Of course, the fish will flow away and the boats will not be there, but we are still moving in the right direction, right? I hope. So it will be fully automatic. When you put in your request, it will be automatically processed and provide you with the result. No, fish doesn't swim that fast. It's a separate, difficult theory. These schools of fish are not static, because fish are concentrating in those schools. It's a separate story, but we are no biologists, and at this level it's too hard for us to do the analysis. We need to first sort out other things. First we need to train the neuronic network. For that we need to have at least 20,000 samples. More questions? Have you looked at the radar images? No, we cannot see fish in the deep with radar images. But this slide shows that most of it can be detected by this. At least they're actively used here. Thank you once again for a very interesting presentation.